April 8, 1943, 27,000 feet above Koblenz, Germany. Second Lieutenant Robert "Bobby" Johnson feels the first shutter run through his P-47C Thunderbolt at exactly 14:27 hours. The Pratt & Whitney R-2800 double wasp engine, all 2,000 horsepower of it, coughs once, twice, then begins trailing a thin stream of white smoke that turns black as oil pressure drops like a stone. The cockpit temperature gauge climbs past the red line. Johnson's gloved hand moves instinctively to the throttle, easing it back, but the damage is already done. A 20-millimeter cannon shell from the Focke-Wulf 190 that bounced him over Cologne has found something vital deep in the engine's 18 cylinders. "Red 3 to red leader," Johnson transmits, his voice steady despite the sweat running down his spine. "I'm hit." Engines cooking, breaking formation. The radio crackles with acknowledgement, but Johnson is already alone. At this altitude, in this sky, every pilot knows the mathematics of survival. The P-47 is a beast, 7 tons of American engineering that fights like a heavyweight boxer, but even heavyweights go down when you hit them in the right place. Johnson rolls the stick forward, pointing the Thunderbolt's broad nose toward the west, toward home, toward England, 300 miles away across hostile territory. The engine temperature continues climbing. At 450 degrees Fahrenheit, something inside the power plant makes a sound like a hammer striking an anvil. The propeller windmills uselessly, and suddenly, Johnson is flying a 7-ton glider with the aerodynamic properties of a brick. He crosses the German border into Belgium at 18,000 feet, losing altitude at 600 feet per minute. The Belgian countryside spreads below him, a patchwork of brown fields and gray villages connected by narrow roads. Johnson scans the horizon for somewhere, anywhere, to put down. The P-47 has earned a reputation for bringing pilots home even when shot to pieces, but without power, even the Thunderbolt obeys Isaac Newton. At 8,000 feet, Johnson makes his decision. A farmer's field outside the village of Eupen, just across the German-Belgian border. Long enough, flat enough, maybe. He cranks the landing gear down manually, feeling the mechanical resistance through the hand crank. The massive main wheels lock into place with reassuring chunks. Johnson tightens his shoulder harness until it cuts into his flight suit, plants his feet firmly on the rudder pedals, and begins his approach. The Thunderbolt comes in hot. No power means no control over descent rate. Johnson holds the nose up as long as he dares, bleeding off speed, waiting for the stall warning buffet. The field rushes up. At the last possible second, he flares, and the main gear kisses Belgian soil with surprising gentleness. Then, physics takes over. 7 tons of fighter aircraft traveling at 90 miles per hour encounter soft spring earth. The main wheels dig furrows 2 feet deep. The tail comes up, and for one terrible moment, Johnson thinks he's going to nose over, but the Thunderbolt settles back on all 3 wheels. 50 yards later, the landing gear collapses, struts never designed for this kind of abuse finally surrendering, and the fighter's belly hits the ground with a shriek of tortured metal. The P-47 slides another 100 yards on its belly, plowing a groove through the Belgian topsoil, before finally shuddering to a halt in a cloud of dust and the smell of hot metal and aviation fuel. Johnson sits in the cockpit for 5 seconds, listening to his own heartbeat, before popping the canopy and scrambling out. His boots hit the ground just as he sees them, 4 Wehrmacht soldiers emerging from the tree line, rifles raised, running toward him across the field. There will be no escape and evasion today, no stolen bicycle ride to the coast, no pickup by the underground resistance. Johnson raises his hands above his head and watches as German soldiers surround the P-47 Thunderbolt that will never return to England. What Second Lieutenant Bobby Johnson doesn't know, what he cannot possibly know as they march him away toward a prisoner of war camp, is that his crippled fighter is about to deal a more devastating blow to Nazi Germany than 1,000 successful bombing missions. April 10th, 1943. Eupen, Belgium. Hauptmann Friedrich Schiller of the Luftwaffe Technical Intelligence Service stands in the Belgian field, circling the downed P-47 with the careful attention of a jeweler examining a rare diamond. He's been chasing reports of American fighters for 6 months, collecting fragments and scraps, interviewing pilots who've tangled with the Thunderbolt at altitude. But this is the first time he's seen one intact. Remarkable, he mutters, running his hand along the armored cowling. The morning sun glints off the olive-drab paint. Bullet holes stipple the wings and fuselage, evidence of the running fight that brought it down, but the fundamental structure remains sound. More importantly, the engine is still attached, the Pratt & Whitney R2800, the American's secret weapon. Schiller has read the intelligence reports. He knows the specifications on paper: 18 cylinders arranged in 2 rows of 9, air-cooled, producing over 2,000 horsepower at takeoff. The numbers seemed impossible when he first saw them. German engineers had dismissed them as American propaganda, the kind of inflated claims that plague wartime intelligence. But now, Schiller places his hand on the massive engine cowling and feels the physical reality of American industrial ambition. "Can we move it?" asks Oberleutnant Werner Krebs, Schiller's assistant, a former Messerschmitt test pilot who understands the value of captured enemy technology. "We have to move it," Schiller replies. "Get me a transport, a big one. I want this aircraft in Rechlin by the end of the week." Rechlin. The word carries weight among Luftwaffe personnel. The Erprobungsstelle Rechlin, the Reich's primary aircraft testing facility, located on the shores of Lake Müritz in northern Germany. If you want to know what an enemy aircraft can truly do, you take it to Rechlin. If you want to understand how the enemy thinks, how they build, what advantages they possess, Rechlin is where secrets are revealed. The logistics prove challenging. The P-47 weighs over 6 tons, and even with the landing gear collapsed, moving it requires specialized equipment. Schiller commandeers a heavy transport truck from a Wehrmacht engineering unit and a crane from a Belgian railway depot. German soldiers work through the night, attaching chains and lifting straps, winching the fighter onto a reinforced flatbed truck. Local Belgians watch from windows and doorways, their faces carefully neutral. They've learned to show nothing. Not joy at German difficulties, not sorrow at American losses. They watch and they remember. And they wait. By dawn on April 11th, the convoy is ready. The P-47 rides on the flatbed, covered with camouflage netting, accompanied by 2 trucks of guards and Schiller's staff car. They move slowly, avoiding main roads where partisan attacks are common, taking rural routes that wind through the Ardennes forest. At a checkpoint near Aachen, a young Wehrmacht sentry stares at the massive fighter aircraft rolling past on its trailer. "What is that?" he asks his sergeant. "American," the sergeant replies, spitting into the dirt. "One of the new ones, the kind that's been shooting up our airfields." "Where are they taking it?" "Somewhere they can figure out how to beat it," the sergeant says, but his voice carries no conviction. He's seen too many wrecked Messerschmitts hauled back from the Western Front, too many funerals for pilots who ventured up to meet the American bomber streams. The convoy crosses into Germany proper on April 12th. By April 14th, after 4 days of careful transport, avoiding air raids and navigating bomb-damaged roads, the P-47 arrives at Rechlin's main gate. Oberingenieur Klaus Weber is waiting. April 14th, 1943. Erprobungsstelle Rechlin, Germany. Klaus Weber has been an aircraft engineer for 23 years. He built his first engine at 17, a modified motorcycle power plant that won him a scholarship to the Technical University of Berlin. By 25, he was working for Daimler-Benz, designing cooling systems for the DB601 engine that powered the Messerschmitt Bf 109. By 30, he'd been recruited to Rechlin to analyze and test enemy aircraft that fell into German hands. He's examined Spitfires and Hurricanes, studied the Rolls-Royce Merlin engine until he could sketch its internals from memory. He's crawled through the wreckage of British bombers, traced fuel lines and electrical systems, written reports on British manufacturing techniques and design philosophy. He's seen the best that Britain can build. But nothing has prepared him for the P-47 Thunderbolt. Weber circles the fighter slowly, notepad in hand, making preliminary observations. The aircraft dominates the hangar, bigger than any single-engine fighter he's ever encountered. The fuselage is massive, barrel-shaped, built around that enormous radial engine. The wings are thick, solid, containing fuel tanks that dwarf anything in the German arsenal. "It looks like they built a fighter around a bomber engine," observes Lieutenant Hans Drescher, Weber's chief mechanic, a man who spent 30 years working with aircraft engines and speaks with the authority of experience. That's exactly what they did," Weber replies. He taps his pencil against his notepad. The question is how, and more importantly, how well. The disassembly begins the following morning. Weber's team, 6 master mechanics and 3 specialist engineers, approaches the P-47 with systematic precision. They photograph everything, every panel, every fastener, every scratch and dent. The documentation must be complete because this aircraft is worth more than gold. It's worth knowledge. They remove the cowling panels first, exposing the Pratt & Whitney R2800 in all its glory. Weber has seen photographs and intelligence reports, grainy images taken by spies and informants. But photographs cannot convey the physical presence of this engine. Drescher lets out a low whistle. Mein Gott! The R2800 dominates the forward fuselage like a mechanical heart, 18 cylinders arranged in 2 radial banks, each cylinder head finned for cooling, the entire assembly larger than most automobile engines. Weber can immediately see the craftsmanship, the precision of the cylinder spacing, the quality of the welding, the sophisticated arrangement of accessories and systems clustered around the main block. "Start the measurements," Weber orders. "I want exact dimensions of every major component." For 3 days they measure and document the bore and stroke of the cylinders, the displacement, 2,804 cubic inches, nearly 46 liters, the compression ratio, the weight, 2,360 pounds for the engine alone. Every number goes into Weber's growing report, but numbers alone don't tell the story. On April 18th, they begin the actual disassembly. Weber personally removes the first cylinder head using a specialized socket wrench to crack the cylinder studs. The head lifts free with effort, revealing the piston crown and valve assembly inside. He sets it carefully on a padded workbench and leans in close with a magnifying glass. The piston crown is scorched black from combustion, but underneath the carbon deposits, Weber can see the metal itself. He scrapes away some carbon with a dental pick, exposing the alloy beneath. Even to the naked eye, it's clear this isn't ordinary aluminum. "Bring me the hardness tester," Weber calls out. Drescher delivers the Brunel hardness testing equipment, a precision instrument that measures metal hardness by pressing a hardened steel ball into the surface. Weber makes 3 measurements on the piston crown, then checks his reference chart. "Impossible," he mutters. "What is it?" asks Drescher. "This alloy." Weber taps the piston with his fingernail. The hardness reading indicates a high-temperature aluminum alloy with significant additions of copper, nickel, and probably molybdenum. "We've experimented with similar formulations, but we abandoned them because we lacked the raw materials. The Allies control most of the world's nickel production. We've been rationing nickel for U-boat construction." Weber makes a note in his log. Pistons manufactured from superior high-temperature alloys unavailable to German industry due to strategic material shortages. It's the first crack in the dam, the first hint that this investigation will reveal problems far larger than engineering challenges. April 22, 1943, Rechlin testing facility. The supercharger assembly requires an entire day to extract from the engine. Weber's team works with surgical precision, disconnecting oil lines, removing mounting bolts, carefully lifting the massive 2-stage supercharger from its housing at the rear of the engine. When they finally set it on the workbench, Weber simply stares. The supercharger is a masterpiece of mechanical engineering. 2 centrifugal compressor stages connected in series, each stage driven by exhaust gases through a complex turbine assembly. Between the 2 stages sits an intercooler, a heat exchanger that cools the compressed air before it enters the second compression stage, dramatically increasing efficiency and power output. Weber has seen German attempts at 2-stage supercharging. He's read the reports from Daimler-Benz and Junkers, studied their experimental installations on test engines. Every German attempt has encountered the same problems: complexity, reliability issues, weight penalties that outweigh performance gains. The official Luftwaffe position is that two-stage supercharging is theoretically sound, but practically impossible to implement in a combat aircraft. Yet here it sits. Not theoretical, not experimental. Production equipment, mass-manufactured, installed in an operational fighter aircraft that's flown combat missions over Germany. How did they solve the intercooler problem? Asks Friedrich Bauer, one of Weber's specialist engineers, a man who wrote his doctoral thesis on supercharger thermodynamics. Weber examines the intercooler core, a compact assembly of thin-walled tubes and cooling fins. He measures the tube wall thickness with a micrometer. 0.035 inches, he announces, thinner than cigarette paper, the manufacturing precision required to produce these tubes without leaks or weak points. He trails off, picking up his magnifying glass to examine the tube-to-header joints. The brazing work is flawless, no gaps, no flux residue, no signs of the quality issues that plague German production facilities working with increasingly unskilled labor and material shortages. Pull the manufacturing data plate from the engine, Weber orders. I want to know when this engine was built. Drescher returns 15 minutes later with a rubbing of the engine's data plate. Weber studies the information, manufacturer codes, serial numbers, production date. December 1942, Weber reads aloud. 4 months ago. This engine was built 4 months ago at Pratt & Whitney's main facility in East Hartford, Connecticut. The timeline settles over the team like a cold fog. 4 months from manufacture to combat operations over Germany. That means assembly lines, mass production, hundreds, perhaps thousands of these engines rolling off American factory floors every month. Weber moves to the crankshaft next, the massive forged steel shaft that converts the piston's linear motion into rotational power. It requires 4 men to lift it onto the measurement table. Weber's calipers measure the main bearing journals, checking for concentricity and dimensional accuracy. The tolerances, he says quietly. Drescher, check my measurements. The chief mechanic performs his own measurement sequence, then checks the numbers against Weber's figures. Plus or minus 0.002 inches, Drescher confirms. On a crankshaft this size under mass production conditions, that's impossible, Weber finishes. That's what it is. Those tolerances require specialized grinding equipment, skilled operators, quality control systems. We can achieve similar precision in a laboratory, building prototype engines one at a time. But in mass production? He thinks of the German aircraft engine factories he's visited. Plants running 3 shifts with workers who learned their trades in 3-week crash courses. Bombing raids that disrupt production for days at a time. Quality control inspectors stretched thin, unable to catch every defect. The gap between German capability and American achievement yawns wider with every measurement. The connecting rods reveal another shock. Weber examines the rod-to-crank bearing surfaces under magnification, checking for the characteristic wear patterns that indicate bearing quality and lubrication efficiency. What he finds makes him call Bauer over for a second opinion. The bearing surfaces are mirror smooth, Bauer confirms. No scoring. No hot spots, no indication of lubrication breakdown even under high-power operation. The oil analysis will tell us more, but preliminary examination suggests they're using a superior lubricant formulation. Weber drains a sample of oil from the engine's sump into a clean glass beaker. Even to the naked eye, the oil appears different from standard German aviation lubricants, clearer, less viscous at room temperature. Laboratory analysis later that week will confirm the presence of advanced synthetic additives that German chemists have theorized about but never successfully manufactured at scale. By April 25th, Weber's preliminary report has reached 30 pages of dense technical analysis, but the most damning evidence comes from the simplest observation. Standing in the hangar, looking at the partially disassembled P-47, Weber does mental arithmetic. The fighter contains approximately 15,000 individual parts, rivets, bolts, hinges, electrical connections, hydraulic fittings, each part manufactured to exacting standards, each part inspected, approved, assembled by workers in American factories operating under conditions that German industry can only dream of. Full employment, abundant raw materials, factory floors safe from bomber attack, skilled workers who go home to dinner rather than air raid shelters. How many of these do you think they're building? Drescher asks, echoing Weber's thoughts. Weber has read the intelligence estimates, American aircraft production figures that seem to defy economic logic. The reports say Republic Aviation is producing 300 P-47s per month at their Farmingdale facility. Weber replies, they're building a second factory in Evansville, Indiana, that will add another 200 per month when it reaches full production. 500 fighters per month, Drescher says slowly, from just one aircraft type. Plus the P-51 Mustangs, plus the P-38 Lightnings, plus the bombers, B-17, B-24s by the thousand. Weber's voice is flat, clinical, but inside, something is breaking. The engineer's faith in German technical superiority, carefully cultivated through years of propaganda and genuine achievement, is crumbling under the weight of evidence. That evening, Weber works late in his office, drafting the report that will eventually reach Reichsmarshal Hermann Göring's desk. He chooses his words carefully, knowing that telling powerful men uncomfortable truths requires diplomatic language. But some truths resist diplomatic phrasing. Weber writes, the captured P-47 Thunderbolt represents a level of engineering sophistication and manufacturing capability that exceeds current German production standards in every measurable category. The engine's advanced supercharger system, superior materials, and exceptional build quality are not the result of German intelligence failures or Allied good fortune. They represent a fundamental industrial advantage that cannot be overcome through improved tactics or increased effort alone. He stops writing, staring at those words. They're a death sentence for German hopes of air superiority. They're also the truth. May 3, 1943. Rechlin Airfield, Hauptmann Hubertus von Bohnen pulls the captured P-47's cockpit canopy closed with a satisfying click and surveys the instrument panel before him. Von Bohnen is one of Rechlin's senior test pilots, a 40-mission veteran of the Eastern Front who's flown everything from elderly Heinkel biplanes to the latest Focke-Wulf 190s. His job is simple. Fly captured enemy aircraft, push them to their limits, and report what German pilots need to know. He's flown Spitfires and Hurricanes, even a captured P-38 Lightning. But the P-47 is different. Sitting in the cockpit, von Bohnen feels like he's strapped into a flying fortress. The cockpit is spacious, almost luxurious by German standards. The seat is comfortable. The visibility is excellent through the bubble canopy. Even the oxygen system feels robust, professional, designed by people who expected their pilots to survive. Rechlin Tower, this is Test 59er, von Bohnen transmits. Request permission to taxi. Test 59er, cleared to taxi runway 23. Wind calm. Von Bohnen advances the throttle, and the Pratt & Whitney R-2800 responds with a deep, thunderous roar that vibrates through the airframe. The P-47 rolls forward, surprisingly nimble for its size despite the tailwheel configuration. Von Bohnen uses gentle touches on the rudder pedals, feeling out the fighter's ground-handling characteristics. At the runway threshold, he performs his final checks. Oil pressure, good. Fuel mixture, rich. Propeller, full increase RPM. Flaps, 10 degrees. Trim, neutral. Everything reads normally, though the American gauge, faces, and English labels required an hour of cockpit familiarization before the flight. Rechlin Tower, Test 59er ready for takeoff. Cleared for takeoff 59er. Good hunting. Von Bohnen pushes the throttle forward to maximum power, and the P-47 Thunderbolt roars down the runway. The acceleration is ponderous at first. 7 tons of fighter takes time to build momentum, but by mid-field, the tail lifts, and von Bohnen can feel the wings beginning to generate lift. At 90 knots indicated airspeed, he eases back on the stick, and the Thunderbolt rotates smoothly into the air. The gear retracts with solid mechanical chunks. Von Bohnen establishes a climb attitude, watching the airspeed build as he pulls the fighter skyward. The R-2800 pulls without strain, the manifold pressure rock steady at 48 inches, the cylinder head temperature well within limits. This engine was designed with margin, excess capacity built in for reliability. At 10,000 feet, von Bohnen levels off and begins his evaluation sequence. First, the basics. He rolls the P-47 left, then right, feeling the aileron's response. Heavy. Heavier than a BF-109 or FW-190. The roll rate is adequate but not exceptional. The P-47 is not a dogfighter's aircraft, but when von Bonin pushes the throttle forward and points the nose down, everything changes. The P-47 accelerates like a falling anvil. The airspeed indicator winds up rapidly, 200 knots, 250, 300, 350. The fighter's heavy wing loading and 7-ton mass become advantages in the dive. Von Bonin levels out at 4,000 feet, having covered 7 miles in less than 90 seconds. Mein Gott, he breathes into his oxygen mask. He's just experienced what German fighter pilots encounter every day over Germany, the P-47's devastating high-speed diving attack. American pilots call it boom and zoom. They dive from altitude, make one high-speed firing pass, then climb back up beyond the reach of German fighters. Against the Thunderbolt's dive performance, the Bf-109's superior turning ability means nothing. Von Bonin climbs back to altitude and continues his evaluation. He tries various maneuvers, loops, barrel rolls, tight turns. The P-47 is competent but unexceptional in traditional dogfighting. Its real strength lies in the energy game, speed and altitude, vertical maneuvers, the ability to dictate engagement terms. Then, von Bonin tests something that every pilot fears, battle damage simulation. Obviously, he can't actually shoot up the irreplaceable captured aircraft, but he can test its structural limits. He pulls hard on the stick, loading the airframe with G-forces, 4 Gs, 5 Gs, 6 Gs. The fighter shudders slightly but shows no signs of structural failure. Von Bonin has seen Bf-109s shed wings under similar loading, especially late war models built with substandard materials and workmanship. After 45 minutes aloft, von Bonin returns to Rechlin and sets up his approach. The P-47's landing characteristics are straightforward: approach at 110 knots, bleed speed over the threshold, and settle onto the mains with power still on. The touchdown is gentle, the fighter's robust landing gear absorbing the impact without complaint. Klaus Weber is waiting when von Bonin climbs out of the cockpit. "Well?" Weber asks. Von Bonin removes his helmet, his expression thoughtful. "It's not a fighter in the classical sense," he says slowly. "It won't turn with our aircraft. In a traditional dogfight, a skilled 109 pilot should win every time. But," Weber prompts, hearing the unspoken caveat, "but American pilots don't fight dogfights. They fight a different kind of air war, one based on energy, altitude, and survivability. The P-47 is designed for their tactics. It dives faster than anything we have. It can absorb incredible damage and keep flying. And most importantly..." Von Bonin pauses, choosing his words carefully. "It feels like an aircraft built by people who expect to win. Everything about it, the comfort, the reliability, the robust systems, suggests an industrial confidence that we lack." Weber nods grimly. Von Bonin's assessment confirms what the engineering analysis has already revealed. The P-47 Thunderbolt isn't just a good aircraft, it's a symbol of American industrial might, a weapon that succeeds not through engineering elegance or tactical innovation, but through overwhelming material superiority. Over the next week, von Bonin makes 6 more test flights, joined by 2 other Rechlin test pilots. They push the P-47 through increasingly aggressive maneuvers, simulating combat scenarios against Luftwaffe fighters. Each flight produces the same conclusion. In the hands of a disciplined pilot who plays to its strengths, the Thunderbolt is nearly untouchable. The final test flight occurs on May 12th. Hauptmann Ernst Haller, another veteran test pilot, takes the P-47 up for a maximum performance evaluation. He climbs to 32,000 feet, higher than most German fighters can operate effectively, and performs a series of high-altitude maneuvers. The R-280's 2-stage supercharger maintains power output where German engines gasp for oxygen. Haller reports that the aircraft still handles crisply at altitudes where a Bf-109 would be wallowing on the edge of stall. The test flight program ends not because the evaluation is complete, but because the captured P-47's airframe hours are accumulating and fuel for these tests is increasingly scarce. Weber makes the decision to preserve the aircraft for continued ground examination rather than risk it in further flight tests. The Thunderbolt returns to its hangar, Its secrets extracted, its lessons learned, but those lessons offer no comfort. May 20th, 1943. Berlin. The conference room in the Reich Air Ministry is austere, dominated by a large oak table and portraits of Luftwaffe heroes staring down from the walls. Klaus Weber sits at one end of the table, his comprehensive report stacked before him, 142 pages of technical analysis, performance data, and engineering assessments. Facing him are 8 senior Luftwaffe officers and 3 representatives from German aircraft engine manufacturers. General Engineer Adolf Baumker, head of aircraft development for the Reich Air Ministry, opens the meeting. Oberingenieur Weber, we've all read your preliminary findings on the captured P-47. Your conclusions are concerning. Please walk us through the key points. Weber opens his folder and begins. His voice is steady, professional, but everyone in the room can hear the underlying tension. Gentlemen, the Republic P-47 Thunderbolt represents the most significant technological challenge we've encountered in enemy fighter aircraft. Not because it possesses any single revolutionary feature, but because it combines good design with exceptional manufacturing quality at mass production scale. He pulls out a large photograph, the R2800 engine in pristine condition before disassembly. The Pratt & Whitney R2800 Double Wasp produces 2,000 horsepower at takeoff and maintains over 1,500 horsepower at 25,000 feet. This performance is achieved through a 2-stage supercharger with intercooling, a system we explored and abandoned as too complex for series production. Oberst Heinrich Müller from Daimler-Benz shifts uncomfortably. His company had indeed experimented with 2-stage supercharging in the DB601 series, but reliability problems and production complexity forced them to abandon the concept. The Americans haven't just made it work, Weber continues. They've made it work reliably in a production aircraft using manufacturing processes we cannot currently replicate. The tolerances throughout this engine exceed German production capabilities, particularly in crankshaft grinding, cylinder boring, and supercharger impeller machining. He distributes copies of his dimensional analysis, pages of measurements comparing German and American manufacturing precision. The numbers tell a stark story. Where German engines might achieve tolerances of plus or minus 0.005 of an inch in mass production, the R2800 maintains tolerances of plus or minus 0.002 or better. More critically, Weber says, the materials employed in this engine are superior to what we currently use. The pistons are manufactured from aluminum alloys with high nickel and molybdenum content. The exhaust valves are heat-resistant steel alloys that show no signs of degradation after combat use. The connecting rods are forged from premium chrome molybdenum steel. These materials require access to strategic resources that are increasingly unavailable to German industry. Baumker interrupts. Can we develop substitutes, alternative alloys using available materials? We're trying, Weber replies, but substitutes invariably mean compromises in performance or reliability. The Americans aren't making compromises. They have access to global supplies of nickel, chromium, molybdenum, tungsten, all the elements needed for high-performance alloys. The Allied blockade has cut us off from these sources. He moves to the next section of his report. Beyond the engine itself, the aircraft demonstrates sophisticated systems integration. The turbo supercharger system requires precise exhaust gas temperature control. The fuel system incorporates automatic mixture control that adjusts for altitude. The electrical system is robust and well protected. Every system shows evidence of thorough engineering and quality manufacturing. What about production rates? Asks General Major Karl Kohler, representing Luftwaffe operational planning. How many of these aircraft can the Americans build? Weber consults his intelligence summaries. Republic Aviation's Farmingdale facility is currently producing approximately 300 P-47s per month. Their Evansville plant is scheduled to begin production this summer with an initial goal of 200 per month, eventually ramping to 300. Additionally, Curtiss-Wright has been licensed to produce the aircraft at their Buffalo factory. He lets those numbers sink in before continuing. Conservative estimates suggest the Americans will be producing 800 to 1,000 P-47 Thunderbolts per month by early 1944. That's in addition to P-51 Mustangs, P-38 Lightnings, and their bomber production. The silence in the room is deafening. Weber knows what they're all calculating. The Luftwaffe's entire production of all fighter types combined barely reaches 700 aircraft per month, and that number is declining as bombing raids disrupt German factories. Can we copy it? Muller asks bluntly. Can we build our own version of the R-2800? Weber shakes his head. Not meaningfully. We could probably design a similar engine. Our engineering talent is certainly capable, but we lack the industrial infrastructure to mass produce it. The R-2800 requires specialized manufacturing equipment, skilled labor, and materials we don't have. Moreover, copying the engine doesn't solve our fundamental problem. Which is, Baumker prompts. The Americans don't need the best aircraft, Weber says quietly. They need good aircraft in overwhelming numbers. The P-47 isn't perfect. It's heavy. It's expensive, approximately 3 times the cost of a Bf-109. But the Americans can afford expensive. They can produce these fighters faster than we can shoot them down, pilot them with adequately trained airmen, and replace losses faster than we can inflict them. He pulls out another document, casualty projections based on current loss rates. For every P-47 we shoot down, 2 more roll off American assembly lines. The mathematics are inexorable. We're not losing the engineering war. We're losing the industrial war. Von Bonin, sitting in as the test pilot representative, adds his perspective. The captured aircraft flies well. It's rugged and forgiving, but what impressed me most was the evidence of systemic quality. Nothing rattled, nothing leaked, nothing failed. The Americans have achieved what we're struggling to maintain, consistent quality across their entire production run. The meeting continues for another 2 hours, examining every aspect of Weber's report. Representatives from Focke-Wulf and Messerschmitt discuss potential German responses, improved versions of existing fighters, new designs, tactical innovations. But the conversation keeps returning to the same fundamental problem. Germany's aircraft industry is approaching its maximum capacity, while American production is still accelerating. As the meeting concludes, Baumker pulls Weber aside. "Your report is technically excellent," he says quietly, "but it will not be well received at higher levels." The Reichsmarshal does not appreciate pessimistic assessments. "The assessment is realistic, not pessimistic," Weber replies. "We asked for facts about enemy capabilities. I've provided facts. Facts that suggest ultimate defeat," Baumker says. "Be careful how widely you distribute this report." Some truths are dangerous to speak aloud. Weber nods, understanding the warning. In Nazi Germany, telling powerful men they're losing can be hazardous to one's health, but he's an engineer, not a politician. His job is to report reality, not manage egos. The report will eventually reach Hermann Göring's desk, where it will join dozens of other sobering assessments about Allied material superiority. Göring will dismiss it, as he's dismissed similar reports, insisting that German quality will overcome Allied quantity. By late 1943, as American bomber streams darkened German skies, escorted by hundreds of P-47 Thunderbolts, Göring's optimism will seem increasingly delusional. But on this May afternoon in Berlin, Weber simply gathers his papers and prepares to return to Rechlin, where the captured P-47 waits in its hangar, a silent prophet of Germany, June 15, 1943, Rechlin testing facility. The hangar is silent. Under the harsh lights, the captured P-47 gleams like a dissected giant, its engine exposed, metal ribs bare. Klaus Weber runs his hand along a welded seam inside the engine compartment, perfect, flawless, identical to every other weld on the aircraft. Not a prototype, not a showpiece, just standard American production. He thinks of German factories, exhausted workers, rushed welders, inspectors too overwhelmed to check every joint. The Americans, by contrast, are building perfection on an assembly line. Their factory workers, safe, well-fed, unbombed, are winning the war from thousands of miles away. Weber opens his private notebook. We are being defeated not by soldiers or generals, but by factory workers in Detroit. The P-47 is proof that democracy's industry can outproduce totalitarianism's control. We fight with willpower, they fight with mathematics, and mathematics is winning. He notes the data plate, built in December 1942, shot down by April 1943. 4 months from factory to front line, an efficiency German industry can't dream of. They build aircraft the way we build ammunition, he writes, not to last decades, only long enough to win. Finally, he puts into words what he's long feared. Short of a miracle, Germany cannot win. The industrial balance is irreversible. Even writing it feels treasonous. A sound breaks the stillness. Friedrich Drescher enters, toolbox in hand. Working late? Couldn't sleep, Weber replies. My nephew was killed last week, Drescher says, shot down by bomber gunners. He never had a chance. He touches the P-47's armor. I thought we'd learn their secrets, build something better. But that's not really the problem, is it? Weber shakes his head. No, it's not. Drescher stares at the machine. How many more will die before someone admits it? Weber's answer is quiet. Too many. They stand together, two men facing the truth their leaders refuse to see. The war's outcome is already written, in factories, foundries, and production lines thousands of miles away. August 1943. Across Germany, Weber's report on the captured American P-47 spreads through Luftwaffe circles. Some officers quietly acknowledge its truth, others dismiss it as defeatist. At Focke-Wulf, Kurt Tank reads it with weary recognition. His FW-190s suffer from the same shortages and production flaws. He writes, "A good aircraft that exists is better than a perfect one on paper." At Messerschmitt, pride blinds reality. Willy Messerschmitt insists, one German fighter will defeat 3 Americans. But even a 3-to-1 kill ratio cannot offset America's industrial scale. Luftwaffe pilots learn the hard way. The P-47 dives faster, climbs higher, and soaks up punishment their lighter fighters can't. Franz Stigler writes to his brother, "For every one we down, 2 more appear." It's like fighting the tide. At Rechlin, the captured Thunderbolt becomes a pilgrimage site. Some admire its engineering, others sneer at its brute force. Yet all leave uneasy. Germany is fighting an enemy that can build endlessly. September, the Wolf's Lair. Weber presents his findings to Hitler. The Americans have achieved what we cannot, mass production without loss of quality. Hitler interrupts, furious. So you admit German engineers are inferior? Weber answers carefully, not inferior, outnumbered. He's dismissed. Albert Speer later tells him, "You're right," but to admit it would mean admitting the war is lost. October 1943, over Germany. The P-47s now escort bombers deep into the Reich. On Black Thursday, 291 B-17 attack Schweinfurt. The Luftwaffe shoots down 60, but loses 38 fighters it can't replace. Reports describe Thunderbolts shrugging off hits that would destroy a Bf-109. Galland rereads Weber's report and realizes the truth. The Americans have built aircraft meant to survive, not just perform. December 1943, Rechlin Weber's final report concludes, "The P-47 is more than a fighter. It is proof that the Americans have solved the problem of modern war, producing advanced weapons in decisive numbers. Germany builds marvels, but not enough of them. In total war, quantity has its own kind of genius." When the P-47 is sent to Berlin for propaganda display, Weber tells his assistant, "They'll call it a trophy, but it's really evidence of our defeat." May 1945, Rechlin. The war ends. The Soviets seize what's left, including the once captured Thunderbolt. Weber survives, later working for NATO-aligned Germany. In old age, he tells students, "The P-47 taught me that engineering isn't about elegance, it's about the system, design, materials, logistics." The Americans understood that. We didn't, until it was too late. The Thunderbolt's true victory wasn't in dogfights, but in proving that industrial power, not ideology or will, decides wars. Weber knew it from the moment he first examined its engine. Germany had already lost. The rest was just mathematics.